Welcome to Agentic AI World, interview prep for senior AI engineers. I'm your host, and today is episode 28. Today's topic, AI streaming architectures, how to build real-time AI systems that scale. If you're interviewing for a senior AI or ML engineer role, there's a high chance you'll get hit with a question like, how would you design a real-time AI system that processes millions of events per day? This episode gives you everything you need to answer that confidently. Let's break this into three parts: the what, the why, and the how. Part 1. What is AI streaming? Traditional AI pipelines are batch-based. You collect data, train a model, run inference on a batch, and store results. Simple but slow. The world has moved on. Real-time AI streaming means your system ingests live event streams. Think user clicks, sensor readings, financial transactions, chat messages, and makes decisions or predictions within milliseconds. Examples you should know. Fraud detection at a bank. Every card swipe triggers inference in under 50 milliseconds. Recommendation systems. As a user scrolls, the next item is predicted before they stop. Autonomous vehicle perception. Camera frames processed at 30 frames per second. Conversational AI with streaming output. Tokens generated and sent to the user incrementally, one by one. The key distinction an interviewer wants to hear. Batch is about throughput. Streaming is about latency. They're fundamentally different optimization targets. Part 2. Why streaming is hard for AI. This is where most candidates fall short. They know Kafka exists, but they don't know why streaming makes AI hard. Here's your edge. Problem 1. State management. Models often need context. The last 10 messages, the last 30 minutes of sensor data. In streaming systems, you have to explicitly manage this state across a distributed cluster. Apache Flink and Kafka streams give you stateful operators. Know them. Problem 2. Out-of-order events. In distributed systems, events arrive late. A sensor might buffer for 10 seconds before sending. Your model might process event at T plus 5 before the event at T. Watermarking is the solution. You define a tolerance window, say 5 seconds, and hold your stream open that long before processing. Problem 3. Model versioning in flight. You can't just deploy a new model version while the stream is running. You need shadow deployment or blue-green at the inference layer. Some teams run 2 model versions simultaneously and compare outputs before cutting over. Problem 4. Feature drift. The features you extract in real time may diverge from what the model saw in training. This is called training serving skew. The fix. Use the same feature transformation code in both your training pipeline and your streaming inference pipeline. Feast, the open source feature store, was literally designed for this. Part 3. The architecture blueprint. Here's the canonical streaming AI architecture you should draw on a whiteboard. Layer 1. Ingestion. Use Apache Kafka or AWS Kinesis. Events flow in as topics. High throughput, durable, replayable. This is your buffer. Layer 2. Stream processing. Apache Flink or Spark structured streaming. Here you do windowed aggregations, feature engineering, join with enrichment data. Flink is preferred for low latency stateful operations. Layer 3. Feature store, online. Redis or DynamoDB. Pre-computed features are written here by your batch pipeline and read here by your streaming pipeline at sub-millisecond speed. Do not call a heavy database during inference. Layer 4. Model inference. A dedicated inference server, Torch Serve, Triton inference server, or a lightweight fast API service. Receives feature vectors, returns predictions. For LLMs, this is where you handle token streaming using server-send events or WebSockets. Layer 5. Output routing. Push results back to Kafka for downstream consumers, write to a database, or push directly to a client over WebSocket. Layer 6. Monitoring. Track throughput, latency, P50, P95, P99, prediction distribution drift, error rates. Tools. Prometheus, Grafana, and an ML-specific layer like Evidently or YLabs. Part 4. The interview answer framework. When asked, design a real-time fraud detection system. Here's your structure. Step 1. Clarify scale. How many transactions per second? What's the latency SLA? False positive tolerance. Step 2. State your architecture at a high level. I'd use Kafka for ingestion, Flink for feature computation, Redis for feature lookup, Triton for inference, and push results to a decision service. Step 3. Discuss trade-offs. Mention that you're trading infrastructure complexity for latency. Acknowledge Flink has a steep learning curve. Talk about exactly one's semantics. Step 4. Talk about failure modes. What happens if Kafka is down? You buffer at the edge. What if your model goes down? You fall back to rules-based logic. Senior engineers think about failure modes. Junior engineers think about the happy path. Step 5. Mention testing. Shadow mode. Run your new model in parallel without acting on its output. When confidence is high, cut over. Wrap up. Let me leave you with 3 things to remember. 1. Streaming AI is about latency, not throughput. Optimize for time to prediction. 2. Stateful stream processing and feature stores are the 2 hardest problems. Know Flink and feast at a conceptual level. 3. Senior engineers talk about failure modes. Always finish your answer with, and here's how this fails, and here's how we handle it. That's episode 28 of Agentic AI World. If you found this useful, subscribe and hit the bell. New episodes every day. I'll see you tomorrow.